going to start Module 9, and it is on exponential functions. We're going to start with the Explore. So we're going to come over here to the Explore. And it says determine the values of f of x and g of x for the given values of x to complete the table. Okay, we can do that. So right here, 2 times 0, 0, 2 times 1, 2 times 2, 2 times 3, and 2 times 4. Then if I have 2 to the 0 power, I'm going to have 1. 2 to the first power, I'm going to have 2. 2 to the second power, I'm going to have 4. 2 to the third power, I'm going to have 8. And 2 to the fourth power, I'm going to have 16. Now the next thing I want to look at is the rate of change. So how much does this go up by? It went up by 2. Goes up by 2 by adding 2 each time. Each time we do this, we're going to add by 2. So the rate of change I've added by 2. Then we're going to look at the rate of change for g of x. Okay, well, if I was to look at this, I'm adding by 1, I'm adding by 2, I'm adding by 4, and I'm adding by 8. 1, 2, 4, 8. 1, 2, 4, 8. So, if I'm looking at this, this has a constant rate of change, and this has an, what do I just say? Not a constant rate of change. That means that this is linear and this is nonlinear. Okay, so let's look at the next one. We already answered that one. Rewrite each rate of change for g of x as a power. So what it's wanting us to do, from going from 1 to 2, where are we? If I went from 1 to 2, 1 to 2, that's here, isn't it? From 1 to 2, sorry. Oh, let's talk about this first. 0 to 1, 0 and 1. Intervals between 0 and 1. Oh, that's interesting. Why is it doing this? There we go. To 0 to 1, 2 to the 0. Oh, I know what it's saying. Okay. So, this right here, 1 is the same thing as 2 to the 0 power. Now I know what it's talking about. This right here is the same thing as 2 to the first power. This right here is 2 to the second power and 2 to the third power. Okay, so I'm going to come down here, I'm going to write that. Sorry, I was confused on what they were wanting. Okay, so do you notice how This exponent is this one right here. This exponent is this one right here. Okay, so this next question is, what is the rate of change from 9 to 10? So that would be 2 to the 9th power. Sorry, I was boggled. Okay, so now we're going to be talking about exponential. Okay, let's talk some more about exponential. Exponential is going to look like this. Y equals a times b to the x power, where a can't equal 0 and b has got to be greater than 0 but not equal to 1. And we'll talk more about that in just a minute. So if I'm looking at a linear, then I'm going to have a constant rate of change. Everything stays the same. Goes up and over by the same amount each time. Exponential, however, the rate of change increases by the same factor. Okay? On that last one we just did, it goes up by 2, but a multiple of 2. It doesn't go up by adding by 2, but it is a scale factor of 2. So, we're going to look at this. Earthquakes. The Richter scale measures the energy that an earthquake releases and assigns a magnitude to it. These orders of magnitude can be approximated by comparing them to the explosive power of TNT. Tell whether the set of data displays exponential behavior. So, what it wants us to do is, does it go up? Does it multiply by the same number each time? So let's look at this. To get from here to here, we could multiply that by what? 10? We could multiply this by 10. This right here, multiply it by 10. Each time we do this, we're multiplying by 10. Okay? Each time we're multiplying by 10. So, since we are multiplying by a number, not adding a number, but we are multiplying by a number, that means that we have an exponential behavior. It is an exponential behavior. Okay, so now we're going to look at this. In 19th century, psychologist, I don't know how to pronounce that, created a formula to approximate how quickly people forgot information over time. The approximate percentage of a newly learned information over time. The approximate percentage, I rewrote that twice. A person retains over time is shown in the table. Determine whether the data displays an exponential behavior. So again, remember that in order for it to be an exponential behavior, that means that it has to multiply by something. So as we look at this, can we multiply by something? Okay, so let's look at it. Sorry. There we go. So how do we get 100 times something gets 80? So if I was to divide both sides by 100, that would get me x equals 0.8 or 0.80. Well, would that work? Okay, let's get out a calculator and let's do this. So 100 times 0.8, that will work. Okay, so I multiplied by 0.8. This one, if I multiplied by 0.8, definitely. 64 times 0.8, let's see. Yep, I multiplied to get from here to here. Well, multiplied by 0.8. Let's try it again. Multiply that by 0.8. I would get that. So let's try this last one. Multiply by 0.8. Yes. So, oops. I should be putting 0.08. But, yes, it is. it is an exponential behavior, and it goes up by 0.8. We multiply each time by 0.8. So now we're going to do restrictions on exponential functions. So let's come back to this. So an exponential function, the independent variable is an exponent in the function y equals ab to the x, where a can't equal 0, b is greater than 0, and b can't equal 1. So we're going to start with this right here, okay? So I have a equaling 1 and I have b equaling 1. So y equals 1 times 1 to the x. Well, 1 to any power is still going to be 1, so we have y equals 1. So that is the horizontal line going through 1. So this next one, we changed the a to 0. So y equals 0 times 1.756. And I just randomly picked what the b one was to the x power. Well, guys, 0 times anything is going to be 0. So y equals 0. Okay? So that would be a straight line. So first we started up here. It says a can't equal 0 and b has to be greater than 0. So this one was a equaling 0. You would have a horizontal line. Okay, now here I changed a to a different number. So 2 times 0 to some power. Again, 0 to any power is still going to be 0, and that's going to get me 0 again. But do you notice how it starts when x is greater than 0? That's because you can't have 0 to a negative number. 0 to a negative number is undefined. You cannot do that. So if you were to put 0 to the negative 1, that is undefined. Okay, so that's why it has to be greater than 0. Can't equal 0, I should say, the b value. And then this one, I picked just a random number for a. You could have picked whatever number you wanted. And then I picked 1 for the b value. Okay, so this is going to get us 2 times 1. Okay, so whatever that a value is what the horizontal line is going to be like. So on every single one of these, you got a horizontal line of some sort. So that is why it has those restrictions. Okay, so we have what's called an exponential growth. Okay, this is the growth, I should highlight. Growth function. So if growth function means that the b value is going to be greater than 1. The b value is greater than 1. Then I have decay, and that means it's between here. So guys, that means this is a fraction, okay, between 0 and 1. It's a fraction or a decimal. I could put decimal also. Fraction or a decimal between there. So if I look at this, if I look at the growth, b is going to be greater than 1. When I look at this, the domain is going to be all real numbers. The range is going to be y is greater than 0. Okay, the y value is going to be greater than 0. There's going to be one y-intercept and no x-intercepts. And this is what it's going to look like. As x gets bigger, y gets bigger. Okay? As x gets smaller, y is getting closer and closer to 0. Right here it's 0, but it never touches it. That's why it's called approaches 0. Okay, so we're going to do this. It says, Folding. Oh, let me go over, sorry, I forgot to go over decay. Okay, again, decay is going to be between here. The range, did I forget? No, I didn't. The domain and range are exactly the same as the other ones. There's one y-intercept, no x-intercepts. Again, the exact same. Guys, no y-x-intercepts means not going to go through the x-axis at all. So this one looks like this. So decay, it's decaying. So as the x gets bigger, the y, oops, undo. The y approaches here, but never gets to 0. It never touches that x-axis. Where as the x's decrease, the y's get bigger. Okay? So let's look at this. It says folding. Each time you fold a piece of paper in half, it doubles in thickness. If a piece of paper in 0.5 millimeters thick, then you can determine the thickness of y of a piece of paper given the number of folds x in this function. So it actually gives you the function, so you don't even have to figure out what the function is. Identify the key features of the function, graph it, and then identify relevant domain and range. So, is it growth or decay? So this value right here, that value right there. So we're looking at the 2. Is that greater than 0, or is it between 0 and, can't even speak. Is it greater than 1? Yes, it is. So that means that it is a growth. The domain, we already said all real numbers. Oops, all real numbers. Range, y has to be greater than 0. Okay, y-intercept. So y-intercept, every time you want to find the y-intercept, that means x is equal to 0. So I'm going to go, so 2 to, oops, I didn't mean to do that, parentheses 0. So that changes this right here to 1, so 0.05. So that is the y-intercept. So that is the 0.05. So guess what? We already have that for here. Didn't we already find that? Awesome. So now we're going to plug in these points. So y equals 0.052 to the negative 2. Now, all you have to do, if you have the TI calculator, is put it in straight into your calculator as 0.05 times 2, and there should be a caret button, and put in negative 2. And when you do that, you should get 0.0125. Then, doing the exact same thing we just did, except for this time, when you put it into the calculator, you'll be putting in negative 1. And when you do that, 0.025. We already did it for the y-intercept, so now we'll do it for 1. So this is going to be y equals 0.02 to the first, and that'll get 0.1, and y equals 0.05 to the second power, and when you plug that in, you get 0.2. Okay, so then it wants us to graph it. So if I graph it, I'm going to get negative 2 is at 0.125. So here. And negative 1 is at 0.25. Oh, no. I'm forgetting the first 0. Sorry about that, guys. I was wondering why it was so this is way down here. This is way down here. It's going to hit, oh, no, that's still too close. So my y-intercept is going to be here. So that means, oh, I need to make it even smaller. See how it's getting super duper close, but it's not actually touching. 1 and 2. So it's going to look like this. Okay? So, now when we're talking about the domain here, guys, the relevant domain, are we ever going to have negative folds? No. So that means that x has to be greater than, oh, actually, it's got to be greater than 0. Okay. Now, the other thing is that normally this would be a discrete because we don't actually fold it in halvesies. Or, sorry, we wouldn't do 0.5 folds. We would do 1 fold, 2 fold, 3 fold. So this really should be discrete. This should be discrete. Okay, and the range on this, because we're starting, y on this would be y is greater than or equal to 0.5, because that's the y-intercept. Okay, so let's, oh, we could have kept going. Oops. I already did that. Growth or decay. Is this number right here bigger or smaller than 1? This is a growth. Okay, the domain. Y, oops, that's not domain. All real numbers. Or if we wanted to write it like this, we could. Range. Y-intercept. So y equals 3 to the 0 power, so y equals 1. Okay, the function y equals 3 to the x can be used to model a real-world situation. Sarah wants to crowdfund a film project to spread the word that she shares the page with 3 friends and requests that each friend share it with 3 more friends. The function that models the number of new people given the line to crowdfunding page y given the number of cycles x is defined by y to the 3x. So on this, well, we just found my y-intercept is 1. Well, it's not going to help us. Well, it's not going to be this. We know that for sure. Okay. If I was to put in 5, so y equals 3 to the 5th power. So if I take my calculator and I do 3 to the 5th power, I'm going to get 243. So let's look here. If I put in 5, 243. That's not going to get that one. 5, 243. Ooh, look at that. I think that could be it. Nope, not that. So B has to be the answer. Okay? So relevant range. Well, your domain has to be greater than, that's not domain. Your domain, x has to be greater than, has to be greater than what? It has to be greater than 0, right? Oh, that was a horrible set notation. You can't have less than 0 people. And your range Guys, you're going to have number of people. Okay, so if I did this, if I plugged in 1, 3 to the 0 power would be 1. 3 to the first power would be 3. 3 to the second power would be 9. Oops, y equals 3 to the third power would be 27. So this would be 1, 3, 9, 27, 81, and going on forever and ever. Okay. Exponential decay. So the half-life means that it gets smaller by halves each time of a substance, describes how long it takes the substance to deplete by half. The half-life of caffeine in the body of a healthy adult is approximately 5 hours, meaning that it takes 5 hours for the body to break down half of the caffeine. Suppose the energy drink contains 160 milligrams of caffeine. The amount of caffeine left in your the amount of caffeine Y left in your system after X hours is modeled by this right here. Identify the key features of the function and then graph it. Oh, our graph is horrible. Let's see if it's any better on my other one. There we go. We'll do this one. So all we're going to do is, this is decay because it has a half right here. The domain, remember, is all real numbers. Range is y such that y is greater than 0. Y-intercept. So I'm going to plug that in. So I have y equals 160, 1/2, 0 over 5. So y equals 160, 1/2 to the 0 power, and that's 1, so 160. Okay, so I'm going to put 160 right here. Okay, so then we're going to plug this in. So I do y equals 160, and that's going to be 1/2 to the negative 1 over 5. So I'm going to put that straight into my calculator, if I can get my calculator out. So 160 times 0.5 raised to the, in parentheses, negative 0.2, because that's what 1/5 is. And I get 183.79. Then I do, actually, you know what I'm going to do? I'm going to do this first. So 1/5, I'm going to do it like this. So that's to the 2/5. And the reason that I'm doing this is because in my calculator, I can leave the numbers in as is and just change the exponent. So it makes it, oops, that should be a 2. 5 over 5 is 1. So I'm going to change this to 0.2. So that's going to get me 139.29. And then 0.4. That's 121.26. And 0.6. 105.56. And then 0.8. 91.89. Nope, that would be 0.9. And then do that, delete, and get 80. So then I would just come over here and I would put, well, -1. Well, can you have time that's less than 1? No, you can't have time less than 1. So that means the domain actually has to be x such that x is greater than 0. Well, actually greater than or equal to 0. So I'm going to go to 160, and I'm going to plot 0, 160. And then I'm going to plot 139. It's about here. And then, oh, that's 4. Okay, so if I did 4, that would be 91. So that's about here. I'm actually going to plug it in with, how about I plug in it with 8? So 8 over 5, so 8 divided by 5. So that's going to be, so if it was 8, then it would be 52.78. So 852. If I did 10, that would be 40. So 10 would be 40. And 12 would be 30.1. Nope, 30.3. So 12 is 30. And if I did 14, no, I don't want to do 16. 16, that's 17. So if you see, it's going to get smaller and smaller and smaller and smaller. It's going to get close, 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 close. And there we go. The range is going to be, the highest it's going to get is to 160. So the range is going to be between, it's going to be between 0, less than, and it'll go up to 160. It won't go past 160. Okay.